What's up?
What's up, guys? We're going to talk about our final project today. The optical principle we decided to focus on was interference, and to demonstrate it, we built a spectrometer.
With that spectrometer, we took pictures of different elements. We captured their emission lines. And with those emission lines, we can then see how interference acts differently for different elements.
So the first part that we 3D printed just to get the ball rolling was this handy dandy case. It goes on just like this. Why are you texting Ryan? Why are you texting Ryan? There's the first part. She's a looker.
Take it, Gien.
Got some great grooves going on there. Yeah. What happened to the little snappy piece?
Oh, snappy piece.
Okay, so, I mean, there's really not much to talk
about. Oh, don't sell it short. It's
That's a little big, but not a problem. We're going back to the jeweler tonight, right, babe?
Mm-hmm.
So, you can see this snaps on right there. And it has this little lip that comes over the top.
A little spurrier visor.
Yeah, a little spurrier visor.
So with that, we're able to then attach the scope, and that will affix to the mounting ring.
Mm-hmm.
So that
yeah,
way
this is the mounting ring. Basically, the meat of the apparatus lies in this little dongle thing we got going on here. So we'll talk about the different parts. So in here we have, I don't know if you can see. Get some light on it, yeah. You can see there's a tiny piece of diffraction grating that we positioned so that when this lies flush to the case, it will pop right over the lens. So that little piece of diffraction grating lies right on top of the lens, just like that.
So you need to have the diffraction grating lining up with our slit. We have a slit attachment piece that we will affix to the front. And with that, we need to align the slit opening so that its line is parallel with the diffraction grating. Once they're parallel, then we're able to get a full distribution of the spectrum and have that shine on the lens of our camera.
So this gets glued on here, and this piece gets glued on like this. This angle is important, and that was one of the parameters that we needed to calibrate to make sure that our apparatus was working correctly.
This angle of 31 degrees helps us so that we can capture that first maxima, and that we don't have ambient light coming in from other maxima. So the whole point is to capture each interference pattern of the first maxima for each given wavelength. So now, as you see it line up, you can see the diffraction grating lining up with the lens, and when this is in place,
I'll go ahead and blast it with the light,
and you see our spectrum showing up.
So we're gonna travel with you guys to David's deep dark bathroom that doesn't have a window. God, it's cold in here!
Boom.
Boom.
Told ya.
Nice. So to test our apparatus, we use something called a gas discharge lamp, which is basically just some gas that is isolated inside a glass tube, and that tube is hooked up to a power supply so that a voltage can be applied across it. And as the gas is excited by this voltage applied, then the electrons will jump from their ground states up to different energy levels, and when the current passes and they fall back down, they will release photons of discrete wavelengths that are related to the energy levels through which the electron has just moved. And these will be unique to the element. So basically, the images taken with our apparatus basically reflect what was found using the commercial spectrometer. So then to look into the resolution a little bit more to see how close two bands we could discern from one another.
So to do this, we found the resolution factor, which is a value calculated from the groove density on the grating and the slit width. It's a ratio that determines how much light is incident upon the total number of slits that you would find in the grating. In our case, we came up with a resolution factor of 170, and we ran this in the equation to find out that our theoretical spectrometer resolution should be approximately 1.56 nanometers. Granted, this is a theoretical value. It's based purely upon perfect conditions and having all of the light incident upon a perfectly uniform grating.
So you can see that our setup wasn't exactly perfect because our bands were not perfectly straight. They were curved a little bit, which means that either the diffraction grating was buckled a little bit the way we glued it in, or it just wasn't perfectly parallel for whatever reason to the lens when it was fixed to the case. So to further examine the resolution achieved by our spectroscope, I scaled each image down to the full spectrum image that we took using an incandescent bulb. Let me pull that up here. And so basically what I did is I squished each one to line up its colors with what we knew would be the full spectrum. And then I scaled each of these images to 300 pixels just to cover approximately 300 nanometers in the visible spectrum, so maybe 1 pixel per nanometer. And then I wrote a Python program to sum each of them up, basically the same intensity program that we used in the diffraction lab. And these were the results. I'll just pull up Helium as an example. So you can see that basically these graphs are almost identical. The closest distinguishable peaks on our graph correspond to these little two that I have labeled here.
Those two are the best wavelengths that we could find in order to determine the actual resolution of our spectrometer. These two wavelengths are at 422 nanometers and 501 nanometers, so they have a separation distance of about 9 nanometers. And we can clearly see the distinction between these two peaks, which can give us the conclusion that we are very confident that we can at least distinguish between 9 nanometers. However, we did also an experiment on the sodium lamp. The sodium lamp has a distinction between those two wavelengths of about 0.6 nanometers. And we'll pull up the photo, but when you look at it, you can see clearly the solid line of the sodium, but our camera was not able to interpret the difference between those two wavelengths. Deal. Deal looks great.
In conclusion, we built a spectroscope that works pretty reliably. Very reliably, actually.
Yeah, we proved
for the materials that we were provided.
Of at least 9 nanometers, which we feel is pretty good. Theoretically, it should have been between 1.57 nanometers and 2. And we very clearly were able to see, very clearly, we're able to see a difference of 9 nanometers. And that was the closest to spectral wavelengths that we could find. Besides sodium, but sodium was well below our theoretical value. So,
yeah. So we're proud of our work. Had a good semester. Feel really good about it. Having some positive feelings. Come here, kitty. Come here, Stinky. Stinky. Come on up. Come on up.
Come here, you little. Yeah.